Right, that's okay for me. Well, I can't see you guys anyway, so if you anybody, if I can ask
Side
you,
by side gallery or
Yeah,
in
what
the
you trying to
view
do?
menu at the top right?
Yeah, it's in there. That's that little symbol that looks like next to recording. There should be a
yeah,
view setting that says
I've
side by.
now just got the. I'm going to leave it as is.
I'll leave it as it.
I
Fine.
just got the screen, which is fine. It's working. I'll just talk to myself. But if anybody has a question, and don't raise your hand because I can't see you, just burst straight, or wait until I've finished, and then I'll break out. Yeah. So what I'm going to try and give you then is a basically a journey from my back garden. So as you were kind to introduce, although I have had a career in space and astronomy, I'm actually an amateur observer, have been for donkey's years. I actually got a bit fed up of just visually observing faint fuzzies. Sketching was my thing. And for many, many years, I would just simply sketch away and try and capture all the messiers, which I did manage to finally achieve. And here's an image of M51, which I was quite pleased of at the time. 8-inch Schmidt Cassegrain. That's what I see through my scope. When was that? 2012. So that was my world. With retirement coming up in 2020, I thought, great, more opportunity for astronomy. But around that time, there was clearly a new technique coming onto the astro market known as electronic imaging using the concept of live stacking. Now, I guess most of you are now fairly familiar with all of that through the various scope options that are there. I'll mention the C-Star in a moment, but for those who are perhaps not so familiar with it, live stacking simply allows an image to be acquired from your camera, and then it takes another one, and then another one, and then another one, and gradually stacks each image on top of each other by matching the stars in the image and then using it as a template. And essentially, what you end up is a much better, cleaner image of what the telescope was actually able to observe. Now, in 2020, this was fairly new. People were beginning to do this using DSLR cameras attached and then using software, bespoke software to do this. Since 2020, the world has experienced an absolute explosion in the so-called smart scope. And there are several choices now out on the market from the Unistella, which really opened the market around 2020, through to the Dwarf 3 and the C-Stars that are familiar now with in many astronomy exhibitions. And when I went across to Astrofest this year, I mean, frankly, the older, larger telescopes are gradually giving way to this sort of technology. But in 2020, these did not exist. However, we've also seen a plethora of fairly low cost or even free image processing software that allows you to play with this concept of stacking the image from your camera one on top of the other. When I started in 2020, PixInsight was the app of choice, but it's expensive. I use a Mac, and there were very few choices as an alternative, particularly that was free. There was an application called Cyril, which was fairly early days in its use, but that has really just gone on from strength to strength. And so Cyril as a pre-processing, and now with the free version of Affinity Photo coming out as a post-processing, not only do you have the imaging technology for your telescope, you also have the ability to fairly easily now put the software together to create your photos. Now, before I go through my own journey and my own scope, what are my thoughts on smart scopes in 2026, bearing in mind that these things have moved on? This is actually a compilation of images from smart scopes from a guy called Lester Neo, and actually they're pretty impressive. You can do quite a lot with these smart scope systems like Seastars and Dwarf. Um, and so they will certainly capture images with detail and color versus what I used to sketch, which were literally faint fuzzies, as you saw from my image of Messier 51. They are definitely very good for the casual use or outreach. They take almost no time to simply set up in your garden on a tabletop or whatever on a tripod. They're up and running within a few minutes. They are effectively one half of a pair of binoculars. So if you imagine what you can see through a pair of binoculars, if you imagine just breaking that in half, that's the sort of field of view you get. So they're fairly wide field of view images. And if you do have these things switched on for 2 hours or more, you can get the sorts of images that you're seeing in the background there. You can get colored nebula that you can impress and show your friends. It's definitely an easy introduction into the world of astroimaging because the sort of techniques now that you can take the data from your smart scope and run it through the software are all the sorts of things that professional or higher end amateur photographers will now also take their data through. You'll learn about calibration frames and stacking software and the processing of those images, all the sorts of things you will probably want to do if you want to upgrade your scope at a later date. So it's a great introduction to the world of astro imaging. And of course, at something like £500 now, that it is quite cost effective. I mean, when you think of it, the Seastars are almost, well, they're the same as mobile phones now. And what I think we'll see over the next few years is the same sort of activity as you get with phones is every 2 or 3 years you'll get a new improvement, a new update, and people will then want to move on to the new software, the new scope system, and you'll get a very healthy second-hand market beginning to develop around the use of these smart scopes. But they're not for me. And the reason they're not for me is that my interest is, well, to be perfectly honest, I get a bit bored if I'm imaging longer than about half an hour or an hour. I also have a huge range of objects I want to see in the night sky. I don't want to spend all night imaging a particular nebula, taking data 6, 8, 10, 12 hours, and then processing it when I wake up in the morning. I like to sit with my scope nearby. I'm particularly interested in galaxies, planetary nebula. I want to be able to use my telescope to look at the moon and some clusters. And all these higher resolution imaging activities are rather challenging for smart scopes. So while smart scopes are great, and if I'd had the chance in 2020, I might well have moved immediately onto something like a Seastar. I already had an 8-inch telescope, and so what I was really looking for was an opportunity to exploit the kit I already had, but move into astro imaging rather than astro sketching. So I like to think that what I'm doing now is Seastar on steroids. I'm using very much the same kit. The sorts of telescope software I'm using is exactly what you would use with a Seastar. The company involved in Seastar, for example, ZWO, manufactures the computer that I am using for my own telescope. So it's a very similar system. Just imagine it's Seastar, but I actually have an 8-inch telescope rather than something that's the size of a side of binocular. And I choose to operate through a 2-camera system. So sometimes I want to look at deep sky objects using my deep sky camera. And that gives you on the left-hand side an indication of the sort of field of view I would have with my camera attached to my 8-inch SCT. And then I will want to move on and look at planets or the moon. And so I replace the camera in the scope with a planetary camera, and then I can go on then and do high resolution imaging of planets and lunar targets. So those are my two routes, and I usually have to make a choice each evening as to which route I'm going to go down because I have to modify my setup. So what is my setup? So my 8-inch Celestron SCT, I've had that now for nearly 20 years. I probably do need to clean it at some point in the mirror, but anyway, I'm quite happy with it. And all I've really done is at the back end, I've taken away my visual observing and I've attached a cooled camera. I've attached a small, basically a Raspberry Pi type device called an ASI Air onto the scope, which is my little computer. I'm now attached to a mount. It's a lighter weight mount than I used to have. As I get older, I find some of the mounts are rather heavy to move about. I had an equatorial mount, a Skywatcher, an EQ6, but I found it was a bit of a problem. I don't have an observatory, so I have to essentially set up my scope each time I want to use it, and then when the evening is finished, I have to tear it down and put it back in the garage in bits. So I've now got a Strainwave mount, the AM5. I've got a Skywatcher tripod. I've got a Wi-Fi through here with an extender that allows me to then power it through a battery and then sit inside a slightly warm room. It's a conservatory, but I'm sitting essentially next to my scope, and I will pop out quite often to see what's going on with the clouds and the like. And I run it all on the iPad. I prefer to use the iPad than an iPhone, and I certainly don't use a laptop unless I'm doing planetary astronomy where I have really no choice. And to set the ground scope for the talk, I'm not an astrophotographer. My images I find are attractive for me, but you know, don't pixel peep, as they say. I would imagine my images won't sustain being blown up and put on the side of a house. There's quite a bit of noise in the background, but for what I want to achieve, I want to see and understand the science of the images and then move on. So it's referred to as electronically assisted astronomy, or EAA, and you find that there are quite a few websites for people in my position where we generally define it as imaging for less than 60 minutes per target, and quite often it's 30 minutes per target. Whoops. I'd also like to give you some scope for understanding distances in what we're going to be looking at this evening. Because I find the whole journey from a back garden fascinating, what you can genuinely look at and understand from a normal, mine's a Bortle 5 Sky, nothing particularly special. It's a suburb of Bristol. Not brilliant when I look towards the sky glow area around the centre of Bristol itself, but I can sometimes look north as well, which isn't too bad looking further out. So if I can persuade you to imagine the sun to earth distance is represented by 1 inch, then that's a convenient figure of merit because 1 light year would be 1 mile. So when you hear something like, oh, the nearest star is 4.5 light years away, if you imagine that if the Earth to the Sun distance is 1 inch, then the nearest star would be 4.5 miles away. And that gives you a sense of scale. Whereas galaxies would be over 1 million miles away based on that 1 inch measurement. And although 1 million miles is still pretty huge as a distance to get your head around, in my mind, it's a lot more meaningful than simply saying, oh, it's 1 million light years away. So if I have in my mind 1 inch between Earth and the Sun, what I'm going to show you in the images later on is a little quote mark in the corner of each image to indicate what the distance would be in that scaling. So let's meet the neighbours. Obviously, the moon nearby. Many people will do DSLR imaging of the moon. Seastars will do the moon very, very well. It's actually slightly awkward for me at this scale because My telescope would not quite capture the whole of the moon on the chip. I have to basically do it as a mosaic, which can be a bit annoying. But you can follow the lunar cycle quite well. But what I like to also do is play around with the imaging and then reveal that our nearest neighbor is actually surprisingly colorful. You can saturate the images to bring out the fact that there is color on the moon. It's not just a gray or black and white image. You can bring out the fact that there is titanium-rich regions, generally where the lava-filled seas are located. And then there are orangey areas that simply represent the older iron-rich regions, which are generally linked to the highlands. It's not a perfect analogy, but it does illustrate the fact that there is information content in some of the images you get back, even from the moon. Now, you probably will have heard of the Messier 100 object, 110 Messier objects, but perhaps not all of you will be familiar with what's called the Lunar 100. The Lunar 100 is 100 objects of features of the moon. Some of them are quite large features. For example, I think one of them is, the moon, the Earth glow on the side of the moon. But you can also get features that are much, much smaller, and you work your way around the lunar atlas depending on the terminator. As many of you will realize, the moon, a full moon, is rather boring to observe. Not only is it a very bright light in the sky, like having a neighbor's searchlight set off, you can't get much contrast with a full moon. I will never usually observe a full moon unless I'm trying to take a full moon image. What you really want to observe are shadows, usually along the terminator. And the Lunar 100 is a great way to learn about the moon by hunting out the particular targets dependent on the cycle of the phases. And so it's also forces you to look at some of the physics. So, for example, there is something called Luna 72, L72, which is the Atlas crater. But it's not just take an image of Atlas as a crater. What the Lunar 100 wants you to do is to actually spot the explosive volcanic dark halo pit in the Atlas crater. And so you have to observe it at just about the right illumination in order to be able to pull out that particular feature. And that then allows you to understand a little bit more about what's going on with the moon through both its geology, but also its various aberrations and elongations. So I do find I've now become much more interested in the moon as a consequence of that chasing around. I do like the area of the southern polar region of the moon, particularly with Tycho. Much more interesting when there is a lunation which is not full, because although you get the rays coming away from Tycho on a full moon, I don't find the crater is quite so interesting to look at. And in Clavius, which is my favorite cluster area of the lunar craters, and it's something I used to sketch quite frequently. But why do I call them moon landings? Well, I do struggle to try and see if I can find the Sentinel block, the monolith from 2001. Never managed to see it inside Tycho, which is where Arthur C. Clarke had it first arise. Nor do I manage to spot the Clavius moon base that was in 2001. So, you can have some fun going around the moon and linking them to some of the sci-fi stories that you might have grown up with. There's one with Tintin as well. You can find Tintin, the landing that Tintin had on the moon as well. Of course, there are real moon landings, and though no, I cannot see the Apollo 11 spacecraft on the surface of the moon, but I can at least see the craters that were named after the three astronauts, Armstrong, Collins, and Aldrin, which were the three unnamed craters near to where the lunar landing actually took place. So there's a whole bunch of things you can do with imaging the moon. And then there's a bit of fun. I don't know whether you can spot this. I like to see craters and look at the shadows. I do like shadows running across the crater's surface. But there's also oddities like the face of Albategnis. And I don't know if you can see this feature here, which I've enlarged here. This is supposed to be a face. This is the nose, the lips, the chin, the head, the forehead. So it's a feature that you can see at certain points when the shadow is creeping across the crater. And incidentally, this Hipparchus is where Tintin is supposed to have landed with the Hergé adventures. Moving on to the local patch then. So we're now looking at 10 inches away from my scale. So Saturn is approximately 10 inches away if we're thinking of the 1 inch Earth to the Sun. So again, I quite enjoy touring the local patch. Saturn is quite interesting at the moment with its very thin ring system facing towards us. Eventually, of course, it'll open back out again. Jupiter, you can get some oddities. I don't know if you can see there is a moon here, which was Europa, but it created a shadow right in the middle of the red spot. So Europa sort of photobombed the red spot on that particular evening. You can't get much visuals from Venus, but you can definitely see it's got crescent phases, proving that it's nearer to the sun than the Earth. It's always great looking at the solar cycle and looking at the size of sunspots and describing it to people by showing illustrations of how large sunspots are when compared to the size of the Earth. Quite remarkable sizes for those events. Comets will occasionally come across, and you can spend some time looking at the comets. And then Mars was interesting for me, as was mentioned at the beginning. I did have some opportunities to work on Beagle 2. And Beagle 2 was discovered in about 11 years ago now. It landed successfully on the surface of Mars. Unfortunately, it didn't manage to fully deploy all its solar arrays. So 3 of the 4 were deployed. But now we know that Beagle 2 is sitting on the surface of Mars. And so, yeah, it's nice to look at Mars and think about where it actually is in relation to the surface. Before I then go forward for the rest of the talk, which is about the journey out from beyond the solar system, I want to show an image that I didn't take, but I really want to start the journey in the correct sequence. Because I want to explain where stars begin their journey. And actually, most stars are born out of cold, dark, molecular gas. It's something that is very tricky for my 30 minutes to 60-minute timing to be able to observe. So here is an image that's been taken over, well, it says 23 hours, 30 minutes, 24 hours of imaging has been used to take this particular view of the Taurus molecular cloud complex. And the Taurus molecular cloud complex is quite interesting. It's very dark, very cold, and creates a lot of sun-like stars versus what we will observe in a moment, which is the Orion molecular complex, which is a lot brighter and tends to create much more significant giant stars. And the reason I show this image now is because I wanted to show the one image I have taken of a star that is not yet a star. So we have something here called a T Tauri. It's actually the T Tauri star that was then named as the example of a category of stars that are in the stage of forming, but they are not yet burning hydrogen. So they're not effectively officially a star on the main sequence. They are shining because they are gradually condensing out of that cold molecular gas. You can see much easier on the background image on the right hand side. Gravity is coalescing around something that is therefore getting hotter, more compressed. And as the heat rises in the gas cloud, it reaches a point where it starts to glow, and it starts to glow at quite bright temperatures. It needs to get to about 10 million degrees before hydrogen fusion actually starts. And T Tauri has been going on for about 10 million years in its formation and hasn't yet quite got to that point where it literally switches on and then becomes a full-fledged star. And once you have a full-fledged star, what then follows is what I can then observe. So T Tauri, quite difficult to catch in 30 minutes, 40 minutes, but at least it's an example of a star that is not yet fully on its journey. There are other dark nebulas that are also hiding or where you would find stars beginning to coalesce. But these dark nebula are easier for me to observe because they are silhouetted against other stars that have already started to form and are now showing hydrogen fusion. They're bright, they're burning, and therefore they are ionizing some of the gas in the surrounding areas, which is why you're now seeing a brighter glow against which the dark nebula is silhouetted. So on the left-hand side, we have the, I was just going to say, sorry to come back. T Tauri is 400 miles away. So if you're thinking from Hereford, that's probably Carlisle or thereabouts. So again, if you're thinking 1 inch is Earth to the sun distance, T Tauri is now 400 miles away at Carlisle. So we have the Horsehead Nebula. There is a very faint star beginning to punch its way through as it starts to burn brightly. It forces away the gas and the dust and creates a cavity, if you like, pushing away the stellar dust and gas. A lot of those stars are behind the Horsehead. You can't see it, but one is coming through. In the case of the Elephant Trunks Nebula, one has actually effectively punched a hole through the gas and the dust. There is clearly quite a few slightly around the top, you can just beginning to see the glow at the top of the head of the elephant. This incidentally is called the Elephant's Trunk Nebula because this is supposed to be the head, and then you get this long trunk-like feature coming away from the elephant's head activity. So we have examples here of stars that are beginning to shine through and create their way towards showing light back to us here on Earth. But more normally, people would be looking at places like the Orion Nebula as effectively a stellar maternity center. So here we have something like 1,000 of these younger stars, essentially all beginning to form in and amongst the gas and the dust that was beginning to coalesce. In the case of Orion, it looks quite bright because 4 stars in particular, the trapezium stars, have actually, they're about 3 or 4 million years old, and they have effectively punched through a cavity in the nebulosity and the gas and the dust, some of which you can see on the left-hand side. And really they're sitting in a cavity. And if you look at infrared images, you can see the rest of the gas and the dust behind this region where there are even more stars. But because these are so bright and they're causing ionization of the gas and the dust in the general area, the glare takes away from the fact that there are other smaller stars happening growing behind in the gas and the dust. With the Eagle Nebula, you can see this a little bit more clearly, however, because the gas and the dust is still visible, but it's being shaped. The gas and the dust is being shaped around the stars that are just located in the tips of these plumes of gas and dust. Many of the 5,000 stars in the Eagle Nebula are located above this pillar. And indeed, many of you will know this is known as the pillar of creation. image. It's the one that Hubble and now James Webb Space Telescope has taken. So you here see my sort of image of that versus the James Webb, where these stars are being able to punch their way through the gas and the dust. But I like to think of this very much around the name that's often given to it, which is called the Star Queen. And people will sometimes say, well, no, it's the Eagle Nebula. How is it the Star Queen? Well, the Star Queen can be seen as so. Now, I don't know if you can see that. I now see it all the time, which is the Star Queen. She is there with her head and her hair, and she's reaching up and grasping to the stars that are above her in her nebula. And she has her cloak falling away behind her. So here we are. That's the Star Queen with her head. Her arms are up in the air, trying to capture and catch those stars. And I hope from now on, whenever you see the James Webb Space Telescope, Pillars of Creation, you'll also see the Star Queen reaching up into the sky. So these areas of gas and dust are effectively maternity centers. They're where stars are born. Other places they're born are very similar. On the left-hand side, we have something called the Trifid Nebula. As you can see very much the gas and the dust, but the two stars are beginning to push their way through. In this instance, this star down here, the reason it's blue in the area is this is just reflection. The star itself is shining, but the gas and the dust is simply reflecting the blue light, the light back to us, like the atmosphere reflects sunlight back to us, and the particles in our own atmosphere will reflect that light as blue, which is why we see blue light when we look up in the sky on a blue day. We're doing the same when we're looking into this particular feature here, the reflection. Whereas here, we're looking at ionized hydrogen gas created by the stars in the cluster itself. But they don't all have to be lots and lots of stars. And if we look at the Tulip Nebula, I call it the power of one because the coloring of the Tulip Nebula is largely the ionization through the energy of one star. This star here in particular is causing, it's so bright and hot, it's causing the ionization of this whole gaseous region. And this area is close enough to be ionized by the energy coming from this one star. But it gives and allows astrophotographers the opportunity to color it in ways that make it look very attractive. And indeed, it's called a tulip because of its shape. We'll come back to tulip later on for a different reason. So eventually the stars themselves have heated up and blown away all the gas of the birthing nebula that they were created from, and they start to travel around the galaxy as a group of siblings, if you like, or perhaps, in my thinking, a primary school going up to a university. Effectively, the stars are grouped together and travel before they eventually separate on their own individual journeys. So Messier 25 is a young cluster. They're energetic. They're still pretty near their birthplace. Many of the stars are hot blue, and they're very early in their development. Whereas on the right-hand side, we have the beautiful formation known as Caroline's Rose, named after Caroline Herschel. And here, these are a lot older, whereas Messier 25 was only 100 million years old with about 300 stars. With Caroline's Rose, we're looking at a cluster that still manages to operate as a cluster for over 1.5 billion years. And there's about 1,000 stars in this particular cluster. They've managed to survive their journey around the galaxy mainly because of their gravitational attraction. In some senses, they're very much like a globular cluster we'll look at in a moment. They're obviously not as large in terms of their number, but effectively they're hanging around together because of gravity. But eventually all stars will move away from each other and start their own individual journeys around the galaxy. However, perhaps I can digress with a little bit of a school session and show you something else you can do with images. So I took here an image of Messier 34, a cluster of stars. But what you can do with software now, free software, is actually identify what those stars are. On the right-hand side is a professional analysis of Messier 34 following the Hertzsprung-Russell diagram, which you hopefully will be familiar with. The life story of a star allows stars to operate along what's known as a main sequence. This is the main sequence of stars in the Messier 34 analysis. What we have here are a whole bunch of field stars getting in the way. So these are not part of the cluster, so just ignore those. And what we do have, however, for the cluster is a classical main sequence. Thus the stars, once they've started to burn hydrogen and they've started their journey, will be somewhere, depending on their size, will be somewhere along this main sequence. They could either be fairly cool red stars or fairly hot white or blue stars. Our sun is an average star. It's a G-class star. It's a yellow sun sitting somewhere in the middle. And this will govern the age of a star's life as it moves through its evolution cycle. So main sequence of stars, strong line of hot blue stars in Messier 34, and that tells us something I'll point out in a moment. And there's little evidence of what we'd refer to as red giant branching. And what these two pieces of evidence suggest is that it's a young cluster. It hasn't yet got very old stars in its cluster. It's still moving along as it did at the beginning of its cluster formation. And what's nice from my point of view is looking at my own image, only of half an hour of imaging, and at least I can see this main sequence of stars in my own capture. And again, a little evidence of the red and of course the field stars, which basically get in the way. But when stars do move out on their own, 50% of stars don't travel on their own, they travel in partnerships. And so here's a couple of examples. We have 16 Cygni, two sun-like stars which are orbiting each other, taking about 18,000 years to complete their orbit. And then so-called double-double star in Epsilon Lyra, which is quite an intriguing star because when you look at it through a small telescope or through binoculars, you'll see it again as a double star. But when you then look at it through a higher resolution scope, or in my case, I take a video of the star, you can spot that this, what looks like one star, is in fact two stars. Orbiting each other in 1,000 years, in the case of this one, the lower one 700 years. So we have an example here of a quadruple star system. So it's not just two stars orbiting each other, it's two stars of two stars orbiting each other, if you see what I mean. And these are fairly close to us. They're effectively about 100 miles away, 100 light years away, so fairly close. We can also show that stars move. Because Barnard star is so close to us, it's 6 light years or 6 miles away in my metric, and Wolf 359 is only 8 miles away. These are both red dwarf stars, but you can plot their movement over the years if you take the trouble to do so. I've been plotting Barnard star's movement since the year 2000. I need to do another one this year, but you can see it's definitely traveled across the stars, across the sky. Similarly for Wolf 359, from when I took the observation in 2000 to 2024, I can again see that stars do genuinely move if they're close enough to us. You can prove that stars are on their own journey around the galaxy. Not all stars, however, move around the galaxy in the spiral arms as we are more familiar with. There are a whole bunch of stars which are globular clusters. I like to think of them as ancient secluded citadels of stars. I'll explain why in a moment, but to give you some understanding, this is our galaxy looking edge on. This is where we are in the galaxy, and globular clusters operate in a halo around our spiral disk. And there are reasons for that to do with the formation of the galaxy, which I'll explain in a moment. But this is where we will soon be looking out from our back garden. And we look out onto globulars, and they are, well, they were the bane of my life when I was sketching, because I would really try to sketch what I could see. I love globulars. I think they're the most spectacular image, particularly to see in a telescope, when essentially if you've got binocular viewers on your scope system, you just get this wonderful 3D effect when looking at them. But they're quite far away. So again, on my scale, they're about where a geostationary satellite would be orbiting the 1 inch distance between Earth and the Sun. So, getting further away in our universe. And I like to think of them in terms of cities. So to me, Messier 3 is Athens and Messier 13 is Rome. So why do I say that? I say that because Athens Messier 3, you might be able to see it in looking at the image. It's what's known as a classical globular. It's very measured in the way the stars move fairly regularly away from the core and move out towards the outer core in a very regular pattern. The stars, when you do the analysis, are quite balanced between red stars, cooler red stars, and hotter blue stars. The stars themselves are effectively of an average energy. There's about 500,000 stars of them. They're around 11 billion years old. Whereas when we look at Messier 13, it's a Messier, but much more energetic globular. Although it's older at 12 billion years, it's got much more variation in the type of stars that you have. It's also got a lot more of a random nature in the way the cluster center goes out. There's many more dust lanes. So I keep doing that. Sorry, apologies for that. The dust lanes themselves are much more prevalent. There's you can just about, oh dear, sorry about this. The dust lanes here, you can just see some shapes coming through. There's a well-known effect called the propeller, which you can see in smaller images of the system. Once you actually process it, you quite often take the propeller out, but there's a famous dust or a dark gap between stars in the cluster that forms this particular shape, because the layout of these clusters are much more uneven. So I have Rome. It's much more energetic, much more brash, whereas Athens is much more classical, reserved, and refined. And then I have Sparta, Messier 15. This is really struggling now as a globular. It's 13 billion years old. It's only now got 100,000 stars left. Globulars do leak their stars gradually as they move around the galaxy. Stars get stripped away from globulars. It's got a much brighter compressed core. Effectively, it's got what they refer to as like a core collapse globular. And indeed, it's suggested that there might even be a black hole at the center of the cluster. So it's a much more martial, warrior-like cluster in my own imagination. Perhaps it's time now to think about aliens. Do you want to see an alien? Well, I'm not really thinking about that alien, but I am thinking about globulars. And Messier 56 is indeed an alien. First of all, it's an exceptionally old globular cluster. It's about the same distance as we were looking at with our other globulars, but it's much, much fainter. It's got fewer stars. It's been around almost since the beginning of the universe, but it's going in the wrong way around the galactic halo. And it's an example of a globular cluster that we have captured in the creation of our own galaxy. So, as some of you may know, particularly the Gaia European Space Agency satellite has managed to illustrate the fact that our galaxy essentially has grown by the acquisition of other dwarf galaxies in its journey from zero through to today's Milky Way. And as part of that absorption process, the Milky Way has captured alien globular clusters from existing dwarf galaxies as part of that process. There's an interesting story around this one in that when astronomers were looking at the Gaia data, the Dutch astronomers in the community identified that there seemed to be a point around 8 billion years after the beginning of the universe when the Milky Way met another galaxy, a smaller galaxy to the Milky Way as was then, but not insignificant, and the Milky Way acquired it. And so the Dutch decided that, well, this was an example. They'd found this information by looking at globulars and looking at the fact that they seemed to have stars that were not of the same constituency as our own Milky Way. And so they likened it to the mythology of the Greek god Enceladus. One of the titans, one of the giants, I think it was in mythology, that was fighting the pantheon of Greek gods, and was known as a giant that came through the underworld, forcing its way through earthquake-type events, forcing its way up through, I think it might even be the god of volcanoes. And they felt, well, this was an exact example of a mythology that fitted their bill. And so they called this galaxy merger the Gaia-Enceladus merger. The Gaia-Enceladus event when this unusual galaxy was absorbed by our own Milky Way. But British astronomers who were observing the same event and came up with the same analysis, they decided, well, the shape of that merger was quite important, and the shape of that emerging galaxy was quite important, and so they called it the sausage. So we have the Dutch decided to allude to mythology, and we decided to allude to breakfast. So it's still now called the Gaia-Enceladus sausage merger, and it's believed that Messier 56 was a globular cluster from that alien galaxy. So if you want to look at aliens, you can see them in the night sky. Omega Centauri is perhaps the most famous of those aliens. It's a beautiful southern hemisphere target, clearly not one I can capture. It's only 16,000 light years away, 16,000 miles in my metric, and it's got over 10 million stars inside it. And that actually tells you something about it. Although it's a globular cluster, many now believe it's actually the core of a past galaxy that merged with our own galaxy. And indeed, when you analyze the stars in Omega Centauri, they're not anywhere near like the stars you see in globulars. It still had enough gas and dust inside it to create new stars. So Omega Centauri has many more new stars than you will find in a normal globular cluster. So Omega Centauri is not only is it a captured globular, it's actually the core of a past galaxy. Of course, eventually stars must age and eventually die. So looking at the advancing age process, the first planetary nebula discovered by William Herschel was the Dumbbell Nebula. And this is an example of what happens when a sun-like star reaches the end of its 10 billion year life. It shrugs off its outer atmosphere as it tries to balance gravity versus the energy demands of the star at the heart of the atmosphere. And that gas and that dust is shrugged away, It allows the star in the middle to then try and rebalance itself. In the case of a sun-like star, it rebalances itself out as a white dwarf. It's a fairly gentle ending to its life story. On the right-hand side, however, is the Crescent Nebula, which is much more turbulent. So in both instances, there are stars at the center. But in the case of the Crescent Nebula, the star involved is a Wolf-Rayet star. And as a consequence of that star, it's struggling to balance this throwing off its outer atmosphere versus the opportunity to manage the fusion process in the heart of its own star. And ultimately, that star in the Crescent Nebula will go supernova. But in the process, at the moment, you're getting these ripples of atmosphere from that star being energetically shocked by explosions coming away from that turbulent star at the heart of that cluster. So on the left-hand side, it's a peaceful transition. On the right-hand side, it's much, much more turbulent. Until, of course, eventually stars in the case of the Crescent Nebula will eventually go supernova. So whereas on the left-hand side, a star like our sun will just gradually fade away as a white dwarf. On the right-hand side, they will eventually explode. And so you can see the remnants of a star that exploded 1,000 years ago, the Crab Nebula. I call it the death versus a ghost in the family, because whilst on the left-hand side, we can see the star at the center of the Crab Nebula is still active and kicking. It's a pulsar. It's providing a huge amount of energy still into the overall nebula, which is illuminating it on its expanding outward journey. So this is the outside of the star thrown away as a result of the explosion, and it's remaining hot and visible with the pulsar in the middle. But some stars, many, many years later, we just lose where they are. So we are looking here on the right-hand side at something that's called the Bat Nebula or the Eastern Veil Nebula, and it's a much broader target. In my metric, it's 50 miles across, so 50 light years across of gas and dust, the remains of which is the result of a stellar explosion over 10,000 years ago. In fact, those that you know this one will know that there's an eastern and a western veil. So we're looking at simply one part of it. And for me, with my telescope, I've had to build up a mosaic to capture the size of this particular this nebula. But we don't know where the central star is anymore. Effectively, it is now just a ghost. We see the output from the original explosion, and that, of course, that gas and that dust will eventually cool down and eventually become part of the life cycle rebirth in a future star, which is why people often say that certainly now that we've had several series of stellar explosions across our galaxy, that we are all either made out of star stuff, if you like the Carl Sagan view, or others might just say we're just made out of nuclear waste, depending on whether you're a poet or a realist. We can, of course, see stellar explosions, but we see very few of them in our own Milky Way. We've been waiting now for over 400 years for a good stellar explosion in our own galaxy. One is due any day now, as they say. We haven't seen one, but we can see them in other galaxies. And so you can be alerted to supernova in other galaxies, and then you get your telescope out, you take an image, and in those instances, at the points of the yellow arrows, you can see the star that appears that was not there the day before. So these are supernova that took place in two galaxies over the last few years. And they remain bright for about 3 to 6 months, and then gradually they will fade away back into the background. There are also beasts out in our galaxy. So I showed an earlier image of the Tulip Nebula, but not far from the Tulip Nebula is a star, HDE 226868, and it is the host star for a black hole. In fact, it was the first black hole discovered in our galaxy, Cygnus X1. It was detected, well, from a radio source point of view, we've known about Cygnus X1 for some time, certainly in the 60s towards the early 70s, a very bright radio source in the sky. However, we didn't know where it was located, against which would be the host star in which there would be an orbiting connection. It was only in around 1972 analysis was done of this particular star, HDE 226868, where it was seen to wobble in such a way that when they did the maths for it, there was only one reason why it would have such a pronounced wobble when there was no visible companion star, and that was because there was a black hole around which the star was orbiting. And that is how we discovered Cygnus X1, a black hole that is only 7,000 light years or 7,000 miles, as it were, away from where we are living in our solar system today. Traveling abroad to nearby countries, as I might refer to galaxies, my telescope has a high resolution, so it's very awkward to do a galaxy like M31, which is just so large. I would have to spend quite a bit of time mosaicing the images together. So I've tended to focus on the core of Andromeda, M31. And we're now talking about a distance from our 1-inch scale out to 10 times the Earth-Moon distance. So this is where our first galaxy would be located. Most of the images on the left-hand side, most of the stars you see are foreground stars. It's extremely difficult, in fact, probably impossible for my telescope to see any star in the Andromeda galaxy. It's just simply too far away. So the stars you see on the left-hand side are simply foreground stars, stars in our galaxy that are effectively photobombing the core of Andromeda. But you can definitely see the dust lanes very, very clearly of the spiral arms of Andromeda. But you can do some other cool things as well. The M31 was the galaxy that was used by Hubble to prove that the universe, in some sense, was much bigger than people had thought. There was some uncertainty as to whether the Andromeda Nebula, as it was known at the turn of the century, was actually inside our galaxy or external. And he was able to demonstrate it's external because he was tracking the location of what's called Cepheid variable stars. And using his telescope, his 100-inch telescope, he was able to spot these stars and plot their variation in light. And the Cepheid variable relationship had been found around 1915 or thereabouts by Henrietta Swan Leavitt. And he was able to use the fact that these stars are standard candles, that they are known brightnesses. So if you can spot a star with a variable period that is cycling in a way that mimics variables in our own galaxy, then we have a pretty good understanding about how far away the Cepheid variable must be in another galaxy. Now, I can't see the individual stars in a Cepheid variable star in Andromeda, but I can see the brightness change of a Cepheid variable because it's not a point light, it's essentially a spread light function. And so I think if you see the red circles, some of them you might be able to spot. There are stars inside. And these are the names V19, V2, V11. These are the variables that Hubble had spotted. He found a whole host of them, which he then used to detect and monitor the variability to determine the distance to M31. And so it's a great little experiment to see if I can see as many as he did, and quite a few I can't, as you can see with the red circles versus the black circles. But my scope can capture galaxies that are in our local group of galaxies. So our Milky Way is part of a local group where we're gravitationally bound to about 80 galaxies. Most of them are dwarf and fairly faint, but there are a few well-known bright ones. Obviously, Andromeda M31 is one. It has two companions, M32 and M110, which I'm not showing. But M33, the Triangulum Galaxy, is also a nearby galaxy close to Andromeda, just far enough away and small enough. It's about 60% of our Milky Way's size. And so I can capture the whole thing in a single image, and therefore I can do my 30 minutes imaging and so on. And I get the opportunity then to see the various hot blue stars, the red areas where new stars are being formed. It's a very disturbed galaxy, and part of the reason is it's near Andromeda. Andromeda is having some effect on destabilizing it more so than you might expect were it well away from any other galaxy. And those disturbances are replete across the universe. So here's an image of galaxies that are slightly further away than our local group. We're now looking at two galaxies that are in Ursa Major. They're known as Messier 81 and Messier 82, or Bode and Cigar galaxies. And if I had a wide field of view, as you can see, these two galaxies would fit neatly in such a field of view. I have to image them separately, and I would like to refer to these as essentially countries at war, because you've got two galaxies that are undergoing gravitational interactions that you can observe as you capture the imagery. On the left-hand side, we have something that is almost a classical spiral galaxy. It's a beautiful galaxy, but perhaps you can see that the spiral arms are slightly fuzzy and faint towards the edges. And this is because they're gradually being unwound, and they're being unwound because M81 is interacting with another galaxy, M82, and they're in a bit of a gravitational dance. Now, in the case of M81, it's the larger of the two galaxies, and it's managing to survive pretty well. I mean, this is going to be the big gorilla in the room. This may well have some distortion, but fundamentally, it's going to not be too disturbed. It's going to be M82 that has the real trouble. And we can see already with the Cigar Galaxy, it's got a huge amount of gas and dust interacting in the core of that particular galaxy. It's a bit confusing here. This red region at the top and at the bottom is actually in the middle of the galaxy, pushing out through the polar regions, upwards and downwards as polar spikes, whilst the edge-on part of the galaxy is moving across the field, of which some of this gas and this dust is simply the dust lane of the edge part of the galaxy. But what you can definitely see is a huge amount of disruption going on with new gas and dust forming as a consequence of the gravitational dance. And it's believed about 300 million years ago, M82 got very close to M81 and became gravitationally disturbed at the heart of that galaxy. And no doubt it will have a dance, or eventually it will come back and interact again, and eventually perhaps even pulled apart. For example, consider these two galaxies here. Sometimes people refer to these types of events as, collisions in slow motion. Reality is that galaxies don't really collide in that way. There's an awful lot of space between stars in galaxies. They don't mean that they don't crash into each other. Effectively, they merge. It's almost like an invasion of cultures. As I said earlier on, with our own acquisition of the globular clusters from other galaxies, we've also acquired their stars. So quite a few stars in our galaxy, particularly in the bulge of our galaxy, are stars that have come and can be shown to have come from other galaxies. We, in our own Milky Way, we are effectively a collection of immigrants. We have acquired so many stars from past mergers. It's believed up to 8 or 9 galaxies have merged with us over our own lifetime. And looking at the butterfly galaxy on the left-hand side, we can see an example of 2 galaxies that are gradually coming together, and one will probably pass through the other on the dance as it passes around and eventually merges. On the right-hand side are 2 galaxies that have already gone further than that. It's further away anyway, so it's smaller and fainter, but I hope you can see that on the left-hand side we have 2 galaxies colliding at the top, which this is the Hubble image and this is mine. Whereas here with the Heron galaxy, we're already unraveling the spiral arms of both galaxies, and they're forming these tidal tails of stars as they gradually operate and merge. And there are some wonderful computer graphics showing how stars will merge with each other, very much like murmurations. If you see murmurations of the birds in their flights, how they cluster, they fly, they change their shape. And we're seeing the murmuration of stars as they go through this dance. I particularly like this particular galaxy set because it just has this very attractive result, which is known as the heron, because you're supposed to be able to see the head of the heron, the body of the heron, and then the wings of the heron effectively standing on its legs that you can't see. And yeah, you can sort of see that with my own capture. So that's the heron. But so often galaxies are in clusters, and those clusters merge over time. And there's a further one to throw into that, which is known as the mice. This is even further away at 300 million light years away from us, or 300 million miles in my scheme. And you can see now these 2 galaxies are literally leaving 2 cores of the galaxies left, and then the rest of the stars are simply moving around as separated streams. Eventually, they will probably come together in something like an elliptical galaxy, where the original spiral arms of both galaxies are simply lost. And we get a cluster of stars buzzing around like bees in a hive with no particular arm structure any longer. And this is often the fate of spiral galaxies. They drift towards becoming elliptical galaxies. A brief digression. I wanted to go back to the Whirlpool galaxy because I showed you at the beginning of my talk how I sketched, and this is simply showing you the power of astro imaging. So on the right hand side is my sketch of M51 with the same optics. So the 8-inch SCT, there's no difference. I'm just using my eyeball at the eyepiece. And because my eyeball is not a camera, I'm not able to capture image after image after image after image and build it up. Whereas on the left-hand side, that is the same telescope, the same capable optics, but now with a camera on it. And even after 20 to 40 minutes, you can capture an image as impressive as the left-hand side. Colorful, you can see the shape of the spirals. You can see the fact that in this particular one, we've got 2 galaxies also merging. We have this particular galaxy here, which is now believed to have passed through and beyond M51 and will eventually turn around and come back. And at some point, these 2 will also merge into a single unit. But I just wanted to indicate why I really had to make that move from visual observation to something of an electronic nature, bearing in mind that I watched this build up over the course of half an hour. I'm not sitting indoors watching television or something while the telescope is operating overnight. I'm trying to see on my iPad. It doesn't look as impressive as the left-hand side because that's clearly image processed, but it's not too dissimilar. My image would look very much like that on the iPad. It would just be a lot noisier versus what I can show there. So M51, a dear friend of mine as were in the past, I was so pleased to be able to sketch this one with the two faint globs, as it were, to turn around and say to others, I've seen both parts of M51. And then, 10 years later, I can do something like this on the left-hand side. Here's one that some of you may know, a galaxy. Perhaps if I give you a clue, can I pretend to be the voice that was heralding it? There is nothing wrong with your television set. Do not attempt to adjust the picture. You are about to experience the awe and the mystery which reaches from the inner mind to, and some of you more elderly people online might remember the TV series, The Outer Limits. And indeed, I wanted to look at this one because this is known as the Outer Limits Galaxy. And the reason it's called the Outer Limits Galaxy is because if you ever look at the TV credits on the original TV show, you will see at the very end of the credits, you'll see they use the NGC 891 as the example image. And here am I taking an image that looks pretty similar, color accepted, pretty similar to what was used at the time on one of my favorite programs when I was much, much younger, The Outer Limits Galaxy. And here's another one to think about, Celebrity Watch. Is it a celebrity because it was the first discovered compact galaxy group? Well, the answer is no, but it's still an impressive feat. It's known as Stephan's Quintet. It's a Hickson cluster of galaxies, compact galaxy, of which again there's about 110. So it's part of my 3000 objects is to try and figure out how to capture as many as I can. And this one's a nice little cluster of galaxies. This one here in particular is photobombing the actual cluster, which in physics, these are the ones that are close together. This one is, if you like, a foreground galaxy in between us on Earth and the cluster. But it's a nice compact grouping. And not surprisingly, it was the first image the James Webb Space Telescope took when it was released. And I remember watching Biden take great pride in revealing this was the image from the James Webb Space Telescope. Come back. And yeah, okay, NASA spent 10 billion and I spent, well, a lot less than 10 billion on my system. But, I can sort of say I've got some of what James Webb was seeing. So is that the celebrity? Well, no. And some of you, again, may be very familiar with this story, but Stephan's Quintet does appear possibly on most of your TV screens every Christmas, because every Christmas, I'm sure you will be watching It's a Wonderful Life. And in A Wonderful Life, at the very beginning of the film, you have the senior angels talking about George Bailey, and the fact that he's having some difficulty and so on. And at the very beginning, they are showing this particular image taken, I believe it was from Mount Wilson, and it's flashing away as the angels speak. So next time you watch It's a Wonderful Life at the very beginning of the film, this is Stephan's Quintet that is now used for that movie. Anyway, back to taking the big view of continents in our local universe. So we've gone on a journey from stars through to galaxies, through to merged galaxies, but now we're moving out into continents of galaxies, as it were. And this is one, it's the Leo cluster. It's actually an unusual cluster in that it has a high number of spirals. And as I said earlier on, quite often spirals in groups of galaxies will merge together and eventually form elliptical galaxies. So what we can say about the Leo cluster is it's a fairly young cluster of galaxies because there are quite a few spirals dotted throughout. Not all of these by any means are spirals, but there's quite a few that you can spot. In the overall cluster, there's about 200. I certainly don't spot over 200, but I do spot quite a few if you use the imaging software to then track down what are faint images on your image capture, and it will tell you that that little blob is a galaxy. Another way of looking at the image, however, is to reverse it, to do an inverse of the image, and sometimes that makes things slightly clearer. So here is an image of a second well-known cluster of galaxies called Hercules cluster. And then a third cluster is known as the Coma cluster. And these are three quite well-known densely packed clusters, all of which can be imaged in the scope. And again, half an hour imaging will allow you to capture these sorts of images. And most of the faint fuzzies in here will be galaxies in some shape or form. But I like to try and observe and understand what I'm looking at so I can get a better appreciation as the image is building up. And so I gave you three examples of these clusters. So we have Hercules is a mix of spirals and ellipticals. It's therefore older than Leo, a bit more messy, still evolving. Whereas Coma is mainly ellipticals. We've now got rid of pretty much all the spirals, and the ellipticals are beginning to come together. There is a core, so it means that it's probably a fairly mature, old cluster. But where in our universe are these clusters located? Looking at them at the night sky from your garden is all very well and good, but can we link them to places? And the answer is yes, we can, and we can think about that when we're doing our observing. So here is a map of all the clusters of galaxies in our local universe. This is often referred to as, the cosmic web. You see these clusters of structure. All of these points are galaxies, and they are filaments around us. And then you get these voids of nothingness. So people often say it looks a bit like a sponge. So a bit like a sponge, you see gaps and then you see some structure. But we live here in our local group. Our local group is heading towards the Virgo cluster, which is here, which is gravitationally drawing us towards it. And our own Virgo cluster is being drawn slowly but surely towards groups in Centaurus. But this is the Hercules cluster I was observing. We are looking out across into the universe to see the Hercules cluster at around 300 or 400 light years away. And when we look at Coma and Leo, what we're really doing is we're sort of peaking above the Virgo cluster, which is our nearer cluster. And it's one of the reasons the Virgo cluster of galaxies that you often see in galaxy season, which is what we're beginning to come up to now, the spring period. There are so many galaxies in Virgo is because we are very near to the Virgo supercluster, which is where so many galaxies reside. But we're sort of peaking just towards the right for the Leo cluster and just to the left of Coma. What I didn't realize until doing some research and all of this, though, was the Leo cluster is actually in the Coma cluster and not in the Leo supercluster. It's simply a group of galaxies that are in the general direction of the Leo constellation, but the galaxies themselves are all part of this chain of galaxies in what's known as the Coma Wall, one of the largest structures in our local universe. And we're observing these from a back garden. And then you can go even into more distant continents. I don't know how many of you are familiar with the Shackbasian 1 cluster. It's 1 billion miles away, 1 billion light years in real terms. And you'll be looking at this and thinking, well, where is it? It's all a bit faint. But if you turn it into black and white, it's a little easier. You can zoom in on it and you see it's an extraordinary compact cluster. And if you look at it and compare it with the 200-inch at Palomar, you get a somewhat similar image. And this is really a unique structure. And to think about it is to some extent quite mind-blowing. It's amongst the most compact, dense clusters of galaxies known. Each of these galaxies, they're dwarf galaxies in reality, but they're as far away from each other as we are from our globular clusters. So effectively, these are galaxies that are located where our globular clusters would be in our own night sky. So imagine having a night sky in this particular area. You would just see huge, bright cores of dwarf galaxies in the immediate sky. And the question that is challenging for physics is, how is it that we have so many dwarf galaxies, yet they haven't merged? And it's one of those oddities. Their actual velocities amongst each other in terms of their gravitational dance is actually very, very slow. Therefore, they're not moving towards anyone in particular at any great speed. And the query is why? And it's now believed that there is so much dark matter around each of the dwarf galaxies themselves that somehow the dark matter is simply squishing, it's a technical term, squishing the motions of these individual galaxies to slow them right down so that the gravitational dance is literally happening in ultra slow motion. And as a consequence, they simply haven't merged in the same way that we see them merging elsewhere. And indeed, Shackbasian 1 is the furthest of the clusters that I'm locating tonight. It's in the direction of Ursa Major, but it's twice as far as the Ursa Major supercluster. As I said, 1 billion light years away of galaxies in a slow, slow dance. When you take an image like the Leo cluster and you do your analysis using software that's freely available, you find some surprises. And so you do find that monsters are included even in these images. And if you look at the center of the Leo cluster, quite by chance, there are 3 quasars that have photobombed the image. Quasar 1, Quasar 2, and Quasar 3, which is just about visible. I can see it on my screen, but you may not be able to see it on yours. And these are really very far away. We are looking at the brightest galaxies we have in the universe, quasars, active black holes at the center. And we are observing quasars, which are some of the earliest forms of galaxies. And they are 4, 7, and 10 billion light years away. And we are just about able to observe them because they are so bright in our night sky that they allow enough pixels to arrive at your own scope. And these distances, 10 billion light years away in my metric, would now be, if you Earth to the sun was 1 inch, we're now looking at Voyager sort of territory. The solar heliopause is how far this particular quasar would be located. And so finally, then we move towards the last object I can detect. And in fact, it's the object any amateur scope can see. Sorry, it's the furthest that any amateur scope can see. And actually, those of you with sea stars, you can see it in a sea star. I've seen this image captured in a sea star that required, I think, about maybe an hour and a half of imaging of this particular part of the night sky, and they got the pixels. So we are looking at this object here. It's got a really catchy name, APM 08279 plus, which forget that, but that is just its RA and declination coordinates. And this was something that it's a trick of nature that allows us to see that particular object. And you can probably imagine what that trick is. The trick is it's a gravitationally lensed quasar. So what we have with gravitational lensing, as many of you may know, is that we have an object, a cluster of galaxies between us in Earth and the galaxy or the quasar in question. And the gravitational mass of this cluster of galaxies bends space-time to such an extent that the light rays that come from this particular galaxy are distorted and bent around just like a lens. And some of those lensed elements will actually find their way to Earth as a magnified image. And you quite often see lensed galaxies as strips or squiggles around the cores of big galactic cluster groups. And in this particular instance, whilst I can't see or resolve the galaxy cluster that was sitting between me and this object, which if I show there, oops, me and this object, I can't see the cluster itself because it's too faint, but it is clearly massive. And it's allowed the galaxy light from the quasar to find its way to me. It's 12 billion light years away. So the furthest object generally accepted that an amateur telescope can take, simply because of that one trick of a gravitational lensing of a quasar. Now, when the research was done of this one, even recently, I mean, it was a couple of years ago, the quasar was rather uniquely identified as having an enormous water cloud around it. It's something like 140 trillion times the amount of water that exists on the Earth. Now, I can't really go through the science behind all of that, but what I can say is that that water is not water as in our oceans. It's superheated. It's a water vapor, very highly heated water vapor around effectively the quasar. So the quasar has got this gas and dust. It's energetically charged. It's got these huge energetic spikes, which is what gives us the glow that we can see. But around it, we can detect that there is water vapor. And so in conclusion, I have managed to go from looking at the moon on a cold, dark night to be able to see a quasar enjoying a galactic sauna. So here am I sitting in my galaxy, and the APM is sitting surrounded by superheated water, enjoying its own galactic sauna activity. So I hope across that hour you're going to see that space is indeed very big, and I do like the Douglas Adams observation that space is big. You won't believe how vastly, hugely, mind-bogglingly big it is, etc., etc., etc. You either have to like Douglas Adams or not. But what I do also want to ask you all to think about is that in order to enjoy that sort of experience that I enjoy in my own backyard is only possible because I can see the stars in my back garden. And increasingly, we are facing a real challenge from satellites in orbit, which I can understand why that makes telecommunications so much more straightforward. But unless we have some sensible regulations around what is launched and what is not allowed to be launched, we will soon not be able to see the very night sky that we all strive to see. So please, in your own ways, however you can, keep up the pressure to ensure that there is environmental regulation, not only of mega constellations, but there are even programs out there that will reflect sunlight on demand. So you have an outfit called Reflect Orbital, which wants to be able to say to people, if you've got a party in the evening and you want sunlight for that party, we will have the ability to reflect sunlight to you in the darkness. Never mind what happens to anybody in the local area. So please, however you can, keep the pressure up for regulation. Thanks.
Wow, cool. That was a tour.
So hopefully stopping sharing.
Yeah, and hopefully people are coming back online.
We've got people here.
Yeah, we're all back again. Well, I have to say, Chris, that was a fantastic tour across, well, literally the whole universe. As you say, from your back garden, unbelievable. Yeah, it is. It's such a journey. And I remember when I captured that quasar, and like I say, 12 billion light years away, and it's like, and I found it interesting that it's slightly red coloured, and I thought when I first processed it,
Yeah.
oh yeah, I must have mucked it up. But I went back through it to the color calibration. The first time I see, not only is it redshifted, but it as an optical image, it is actually redshifted.
Yes.
It's like, yeah, this is stuff that you dream of 20, 30 years ago, what the
Well,
scientists are doing.
it finally got to my camera. Yep, yep.
And then, like you say, then Elon decides to stick millions of satellites up, or you get your next door neighbour who decides to put a big spotlight, and it's like, yeah, sod all those photons trying to get across the universe. They can't get the last 100 meters, kind of thing.
Yeah.
Well, I'd just like to ask everybody to give a big reward, thanks, whatever you do, as to say thanks to Chris for that fabulous tour. I can just absolutely staggering. And I'm going to ask you in advance now, Chris, that you must have some other talks tucked up your sleeve, have you?
Sorry, I missed that.
Have you got some other talks tucked up your sleeve?
Oh, I love the one that because I run the U3A. I mean, I sort of run it because I'm interested in the subject. But can I persuade anyone to give any talks? No. So I give talks at that level. So I wouldn't say I'm giving a talk on the basis that I'm professor and I'm an expert in it. But I've actually got, and you probably picked it up from my talk, I've got 4 talks I give on the Gaia satellite and the fact that it's uncovered the history of our galaxy, and our neighborhood, and what I call the Great Attractor, that is in our local area. So yeah, I've got various talks like that.
All right.
Wouldn't
Well,
want to
I'll
meet
be
you.
coming back to you again.
Well, indeed, if as long as I said, I know I've looked at some of your talks, and you have people who are experts in those subjects, and I would not claim to be an expert in Gaia or galactic astronomy. I just,
No.
I read books and watch YouTube the same as anyone else.
But to me, it's sort of down to enthusiasm. If you're interested in a subject, then and you're happy to talk about it. That's all. That's all I want.
Yeah.
Right. Q&A. Any questions from the floor? People got some. I've only got one, but I'll let others sort of make a response if they've got any responses. Anybody out there want to say something?
I'll kick off.
Oh,
yeah, absolutely fascinating talk. Photos and all from your back garden, and such a fascinating exploration of the universe. On average, how many you said about the stacking? How many photos are you stacking in that hour period to get those images?
Nearly always I take 60-second subs. So there'll probably be 30 to 50 subs. If I'm doing a cluster, I'll probably be a star cluster. I might be doing 30 seconds because I don't want to blow the stars out.
Yeah.
But always it's 60 seconds. It's just I could do it for longer, but then I lose more with star trails. Now I could do them less, but then sometimes I lose some of the detail.
Mm-hmm. Are you having to use filters? Or you mentioned obviously you're in Bristol, so yes, that's not exactly.
Bother with light pollution filters because what I need to capture is the maximum amount of light into my scope in order to build up the image within 30 to 40 minutes. So I do use a UV IR filter, just to reduce the bloat of the stars. But I don't use I used to, but I've given up using light pollution filters now. And then obviously for the nebula you have to use HAO2.
Yeah. Yeah.
Oh, sorry, O3, but that's just a dual band. I just use a dual band.
Excellent. Thank you.
I mean, can I ask, people have sea stars now, dwarves? Do they, do they do imaging? Do you do imaging? Because most of my AstroSat
There you go. The
felt
dwarf.
that,
Yeah.
yeah, I mean, my AstroSat thought, oh, imaging, oh, it's too complicated. I'm going to do, oh, I have to. Whereas now it's so straightforward. It really is. Okay, you might spend an hour playing around, with your process because you decide you just want to make it look good. But even with sea stars, you can just switch them on and let the thing do its own processing.
Yeah. And as we was chatting last night, Chris, I mean, I think that whole, family of young kids wanting to be able to get them outside. I know you end up looking at your phone again, but at least they're outdoors. And then within minutes, being able to show something big and bright like Orion or Andromeda, it's like that immediacy instead of. I think we've all been down that path before when you get a telescope out and then people don't know how to focus it with an eyepiece or they can't get the acuity in their eye correct. And they look at it and it's like, oh, it's a little fuzzy grey object. And, you can lose some of the interest. Whereas these kind of stick it on the patio within minutes, you got pretty coloured pictures and everybody's going, oh, wow. I'm blown away by them, and as you said, from the shows each year, they've just brought out the Seastar 30 Pro, and then I've heard about Seastar 70 that's in the wings. They're going to be variations and evolutions of them as time goes on.
And I found in my own case that after so I like to sit with the eye with it building up in live, and then I'm reading about it. I'm on the web reading about what I'm looking at. Then after about half an hour, the improvement is hard to then judge. I mean, you get to a certain level, and all you're really doing is get rid of the noise, and you can use software to get rid of some of the noise anyway. So it's time to move on.
And like you say, if you're like trying to capture that as EAA, of course, then you're going to have more concerns about satellites or an aircraft going across it or something else. So you can't remove that sub because it's already being sort of compounded.
My images are never going to be put up on the wall of the house, in any big way. But I'm following the physics and I'm reading it and I'm thinking, yeah, okay. And then of course, because you're doing it in real time, you're then zooming in on things that you hadn't even spotted. You then say, I didn't. I can see the propeller now in Hercules, whatever.
So what's your next challenge then? What's your next target or?
Well, as I said, I mean, I've got 3,000 on my list, and the trouble is, there's two problems. One is the more you go down the list, the more you start going back to faint fuzzies. But the other thing is, I keep a record. I mean, I keep my stacks because software always improves, and then you're forever going back and reprocessing your images. So you've got the one hand, I'm going fainter, like the Shabazian one. But on the other hand, I'm spending probably time reprocessing the Crab Nebula because I've now learned a new trick to sharpen this.
Well, I'm up to 3 terabytes now, so it's getting quite scary here.
Exactly, and don't get on the Lunar. That just crunches up data.
As soon as you start doing like real time, like say with Jupiter or particularly the Moon, and you're taking literally tens of thousands of pictures, it gets ridiculous. I think I've had a 300 gigabyte SIR file, and it's like you can't even deal with it. The computer starts saying, "No."
Get rid of the images. You just have to admit the Lunar. You've just got to delete it.
Anything else out there? Anybody else? Must be some.
You guys have all got these lovely dark skies.
Well, I say you're not bad with 5, but we're
dark for the wrong reason.
Well, I say it's been very dark for quite a long time because none of us have seen stars. It's like
Yeah, yeah.
Yeah,
It's
we're
wait.
trying to
cloudy
have
as well.
observing sessions, and yeah, well, that ain't gonna happen, is it? Maybe this month, Sarah. You never know.
Yeah, who knows? Who knows?
And then, of course, the clocks go back, and then it's like, oh well, we're not doing any observing because it doesn't get dark until like 10 o'clock. So, oh god, why do we live in this crappy
Why do
country with its crappy weather? And it's like, I want to move to Arizona and have the 250 nights a year, and then I'd be like dead because I'd be observing all night and processing all day. So maybe not. I don't know. Right. Well, if there's nothing else being raised by anybody else, can I just ask everybody to give Chris another big thank you? Superb talk. And now we swap stories there, Chris. I know where you live, and I'm going to come and track you down again for the future because I'd love to have you come back and give another presentation.
Well,
So
anyway,
thanks everybody. I'll call it a day now. I'll be sending some message out soon about the Found Hope Planetarium, and when I get my act together about what we're doing in July to go to Leicester Space Centre. So watch this space.
well, enjoy Leicester.
Oh, have you been there?
Well, yeah, as I said at the talk, I mean,
no, in your but I'm in the Leicester
a
Space
visiting
Centre.
professor there, but
Yeah, of course, yes. Yeah, so we're doing a jolly up there this year, so looking forward to it.
excellent. Okay,
All right, guys.
Thank you very much.
Thank you.
Cheers, everyone.
Thank you.
Fantastic.
Stop recording.